Hi everyone, so in this video we are going to give a little introduction into what are solutions to differential equations, and we'll solve some differential equations that you may have already seen and solved before. So let's first consider what would a solution to the differential equation dy dx equals 2x, what would it mean to be a solution to that differential equation? Well, this means we would like to find the function y whose derivative is equal to 2x. Well, I can think of such a function, namely y is equal to x squared, right? That is a function whose derivative dy dx would be 2x. So that checks out. Is this the only such solution? Is this a unique solution? And as you might expect when finding antiderivatives, the answer is no. This formula that we found up here, y equals x squared, is not the only one. There are plenty of other such solutions. So for example, y is equal to x squared plus 3. That would also have this property, y is equal to x squared minus 27. That would also have this property. So adding a constant on the end isn't going to change the slope. It would just shift the solution up. So in general, we would say that the solution would be any function of the form y is equal to x squared plus c. And so we have an infinite amount of solutions. So the general solution should describe what are all such functions that would satisfy this differential equation. There are an infinite number of such solutions that we can graph over here. And so general solutions are always going to have this arbitrary plus c constant or some arbitrary constant in the solution. So at the end of the day, when we have differential equations of the form dy dx is equal to something which only depends on the independent variable x, well then we can find the general solution by integrating the right side of the differential equation with respect to that independent variable. Certainly our differential equations are going to get more complicated. They'll involve higher derivatives and they'll involve both variables. This is a good starting point for thinking about what solutions might look like. So for the next example, let's consider what is called an initial value problem that we often abbreviate with IVP. So for an initial value problem, we're given a differential equation such as dy dx is equal to 2x and some additional information such as what is one point on the graph of the solution. So when we add some additional information about the function we're trying to solve, such as what are the coordinates of one point, we're no longer going to get an infinite number of solutions. So the first step would be to find kind of this picture that we have on the right side. That would be, let's first describe what solutions look like in general. And we have that represented over here. So that means we have a bunch of parabolas. This plus c is just shifting those parabolas up and down vertically, the vertical axis. And so if we want to find the solution that in particular passes through the point at 0, 4, so that's marked right over here, well, now we've got some additional information. And let's use this additional information to solve for this arbitrary constant c. So we're going to take this point, 0, 4, we're going to plug the 4 in for y, we plug the 0 in for x, and then we solve for c, which is very basic. Here we would see that this arbitrary constant c has to equal 4. And so I can label that parabola right over here. So that's corresponding to the solution that in addition had to pass through that point at 0, 4. And therefore that gave us that the value was c. So now that we found the additional value for c, we notice get a unique solution. So there's only one curve that has those derivatives and in addition passes through that specific point. So we call solutions to these initial value problems a particular solution. And those particular solutions are unique. So we only had one curve in red. And so the solution to these initial value problems are unique. And it's not just the value that we found for C, but it should be the equation for the curve that we have in red. And so that would be y is equal to x squared plus 4. And so it's not always as simple as whatever value we have in the coordinate, that's going to give me the value for C. That just happened to be the case for this example. And the other thing I want to clarify is we call this an initial value problem, but that doesn't require that the given point has to be when the independent variable is 0. So we could be given an initial condition when x is 2, y is equal to 0. And then we can plug that in and figure out what the value of C is, and it doesn't necessarily have to be either of those coordinates. But what is important is for any initial value problem, our solution should be unique. So we shouldn't have any arbitrary constant in our solution. So I have a couple of other examples on the last slide, but this is mostly a wrap of the material, mainly thinking about what are solutions to differential equations, what happens when we throw some initial conditions on, what are general solutions versus particular solutions. And so for the examples we've looked at, certainly solving differential equations is oftentimes going to involve integrals. So on the last slide, I have a couple of examples that in addition to practicing this are going to review some really important integration methods such as integration by parts and substitution. So the quiz that you have is mainly going to be about reviewing those calculus integration methods of integration by parts and integration by substitution. So let's work through a couple of examples that are going to require us to do some integration, and in the process we'll review some methods of integrals that are going to be really useful throughout this semester. And so the first differential equation, dy dt, is equal to 6t over t squared minus 5. So we can integrate this to find the general solution. So we would integrate 6t over t squared minus 5 dt. And now we can consider, well, how can we integrate this? It's not so simple. We've got some operations, and what we definitely don't want to do is just break up and integrate the top and then divide by the integral of the bottom. But we can look at this integral and we see that we have a numerator and we have a denominator, and the bottom of the fraction, the denominator, its derivative is fairly closely related to the numerator, in that the derivative of the bottom of the fraction is a multiple of the top of the fraction. And so for cases like this is where the method of integration by substitution is useful. And in this case, we can set our variable, our substitute w, equal to the denominator, which is t squared minus 5. And that means our integral that we started with, we want to re-express this in terms of w. We've got the bottom we can replace with w. So we have 6t over w dt. And so we also would like to get rid of the other dt's, and we do this by taking the derivative of our new variable w. So we would get dw is equal to 2t dt, and therefore in order to substitute 6t dt, we can substitute that in terms of our new variable w as 3w. So our integral has now been transformed into 3w over w dw. And integrating that would give us 3 times the natural log of the absolute value of w plus c. So we have an arbitrary constant of plus c. And then we want to just be sure that we express our final answer in terms of the variable that we started with, which was t. So we would replace that w with t squared minus 5. So our general solution is going to involve this arbitrary constant. It would be 3 times the natural log of the absolute value of t squared minus 5 plus c. And so the main point here is, if you don't recall this process of integration, please be sure to review it. Okay, and so for number 2, we've got w prime is equal to theta cosine of theta. And so if it's not clear, I think a good first step is just to identify what are the input and the dependent variable in regards to this differential equation. So because we have w prime, that means w is the dependent variable. And when we use the prime notation, it's not clear necessarily what the independent variable is, but we can read that from the right side that it must be that theta is the input. Okay, so to solve this differential equation, to solve for w, we integrate the right side, theta cosine of theta d theta. And if we look at the structure of this integral, it's also not so clear that we can directly just integrate the right side. We have a product, and we're not allowed to just split up integration with products. So I can't just integrate theta, integrate cosine of theta, and multiply the two of them together. So what we actually have here is a product, and what is often a useful tool for integrating products is to use what's called integration by parts. And so with the method of integration by parts, we're trying to undo the result of a product rule. So typically the notation that we use to denote the product is we would say we have an integral of u times v prime. And so just to review what integration by parts says, it says if we are integrating something of the form u times v prime, then it's going to equal u times v minus the integral of u prime v. And so the most critical part of this process is finding what is u and what is v prime. And so looking at our differential equation, we've got a product, for example, theta times cosine of theta. And you don't just want to think that's how we line it up, but it makes sense that one of these would be u and the other one is going to be v prime. And the way that you oftentimes want to think about this is u is going to be something that becomes simpler when you differentiate it. And so if we look at these two possibilities, differentiating theta makes it simpler, while differentiating cosine of theta, that actually doesn't make it any simpler. It turns it into a trig function. So maybe a good first guess might be to try theta as u. And therefore, that means we could let cosine theta d theta be v prime. And so different people might have different ways of organizing your work, but I'm going to organize it like this. So I'm going to define u as theta and v prime as cosine of theta d theta. So to find u prime, we take the derivative of u and get d theta. And to find v prime, we integrate cosine theta d theta. And when we integrate that, the integral of cosine is sine of theta. And we typically do put a plus c when we evaluate these integrals. Because we're dealing with a differential equation here, I'm going to hold off on considering the arbitrary constant until a later stage in the process. Okay, so now let's use integration by parts here. So this would give us the integral of uv prime would be uv minus the integral of u prime v. And now we can plug in the fact that we defined u as theta, and we found v to be sine of theta. And then we're going to subtract the integral of u prime, which is d theta, times v, which is sine theta. So we're going to subtract the integral of sine theta d theta. So we have that w is theta times sine of theta minus the integral, and the integral of sine theta is minus cosine theta. And now we can put on our arbitrary constant. So we get w is equal to theta times sine theta plus cosine of theta plus our arbitrary constant c. So here would be our general solution for this differential equation. And so if you have some questions or your integration skills are rusty, please do be sure to look over these methods. Substitution, integration by parts, partial fraction decomposition is another good method which you may be a little bit rusty with. So after looking these over, take some practice, give the quiz a shot.